Going to go on to chapter 3 now. I'm skipping section 2.6 of chapter 2, which is about linear algebra and graph theory. It's nice material, you might want to look at it, but it's not that central and we're running a little bit behind, so I'm going to skip it. I'm going to go on to talk about inner products. So what's an inner product? Well, you all know about the dot product. If you have a vector x and a vector y, then you all know that the dot product of x and y is x1, y1 plus up to x and y n. And this is an important number. In geometry, it tells you about angles and lengths and things. It comes up all the time. So one of the things, for example, is if you take x and inner product it with itself, you get x1 squared plus xn squared, and that's the length of the vector x squared. Or in other words, the length of a vector is, you take the dot product with itself and you take the square root. Okay, so the notion of inner product is just a generalization of this. It's a generalization, and I might also say an abstraction of the dot product. And what I mean by that, it's a generalization in that on Rn there are more inner products than just the dot product. And I should write that down. On Rn there are many inner products, including just one of them is the dot product. And by abstraction, I mean we're going to do this on an abstract vector space. Not just Rn. All right, so let's look at the abstract part of it first. So what do we mean by an inner product on a vector space V? So remember, when we defined a vector space, we looked at the usual properties of Rn and then made them abstract. So we're going to do the same thing here. We're going to take the properties of a dot product and make them abstract. And then we'll say that an inner product is something with those properties. So basically the first question is, what are the properties of the dot product? Well, let's see. So one of the things about the dot product is if you take a vector v and a vector w and add them and dot them with another vector z, that's the same thing as v dot z plus w dot z. And in the other order too, v dot w plus z is equal to v dot w plus v dot z. And also constants pull out, which is to say if you have a constant, a scalar a, and you take a, v, dot w, that's the same thing as a v dot w, and it works in the second coordinate also. And those two properties, or that collection of properties together, is what's called bilinearity. Or I'll just say bilinear, the bilinear property. Or sometimes you'll say bilinearity. So what does bilinear mean? Well, this is linear because adding over here is the same thing as adding over here. And the bi means that it works on both sides. So there's a linear on the left-hand side and linear on the right-hand side. And similarly, the fact that you can pull scalars out this way on the left is half of the bilinearity, and then they also work on the right of the dot, I should say. That's the other part of bilinearity. Okay, so that's one of the main properties that the dot product satisfies. Another one is symmetry. V dot W is certainly equal to W dot V. And that's, for obvious reasons, called the symmetry property. And the last thing that it satisfies that I'm going to single out is positivity, which is to say, if you take a vector and dot it with itself, that's greater than or equal to 0. It's a real number, and it's greater than or equal to 0, and it's only equal to 0 if v is the 0 vector. Right? Because remember, if v is x1 through xn, then v dot v is x1 squared plus dot 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 xn squared. And this is certainly a number that's greater than or equal to 0. And the only way it can be 0 is if all of the xi's are 0. So that's this part. And this is what's called positivity. And, well, there you basically have it. That's the definition of an abstract general bilinear inner product. All right, so let me just say that. Here's a definition. So what we have is V is a real vector space. And as always, it's real. And an inner product on V is the following. It is, I'll write it like this, for every vector V and W, it's a number. This is a real number. So in other words, it's the inner product is written with parentheses, and if you this takes a vector V and a vector W to the inner product, which is a real number. So it's a way of associating two vectors, a number, and with the properties I won't write them out, but it's supposed to be bilinear, symmetric, and positive. So I won't write those out, but I'll just maybe one or two of them. For example, the symmetric condition is simply that VW is supposed to equal WV. And the positivity condition is that VV is greater than or equal to 0 and equal to 0 only if the vector is the 0 vector. Okay? So, how do you find such things besides the dot product? So, the only example we have at the moment is if V is equal to Rn, and you take the inner product of V and W to be V dot W. That's the basic example. And you should sort of think of that as being sort of prototypical example, but there are others. Well, let's write down some examples. Let's just look at Rn and find examples besides the dot product. Well, for example, I could define xy to be 2 x1 y1 plus 3 x2 y2 plus dot 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 17 x and y n, which is to say I can take the usual dot product and I can just stick in a bunch of scalars as long as they're positive. Here's a non-example. If I took x dot y to be x1 y1 minus x2 y2, that's not allowed. Now, why is that? Well, it's not positive definite. If you took the vector 0, 1 and took its inner product with itself, you would get 0 times 0 minus 1 times 1, which is minus 1. And we don't want to have vectors of negative length. For one thing, I don't know how to take the square root of minus 1, so that's not an example. So that gives a bunch of examples where if you take any n vectors, take any n numbers a1 through an, where the ai's are greater than 0, and you could take, corresponding to that, xy is the summation of the ai, xi, yi. So maybe you should pause the video here for a moment and convince yourself that this is really okay. This really satisfies the conditions 1 to 3. So let's see, condition 2 is obvious, the symmetry is obvious. If you switch x and y, that's clearly gets the same thing. And the positive definiteness is also condition 3, the positivity is also easy because x is summation ai xi squared. And because I assumed the ai's were positive, this is certainly a non-negative number, and the only way it can be 0 is if all the xi's are 0. So the The only thing that requires a little bit of checking is condition 1, the bilinearity condition. So why don't you pause the video and check that. I'll do a couple of more examples in a minute. Let me mention one other part of the definition, which is that if you have an inner product, then associated to that is a norm. You say, all right, double bar, the norm of a vector is defined to be the dot product of the vector with itself to the 1/2, which is to say the square root of the dot product of the vector with itself. Excuse me, not the dot product, the inner product. And this makes sense because this number, VV, is greater than or equal to 0, so you can take its square root. And this is called the norm. Of the vector. Well, let's look at a couple more examples. In Rn, we saw these ones. You take AI, xi, yi, and well, are there any others? And we'll see in a later section, I forget, section 6 or something, there's some sort of discussion of what all of the possible norms, inner products on Rn are. But the answer is that's not all of them. There are others. But now let's talk a little more abstractly. Here's sort of one of the motivating examples of a norm. And what you do is you consider the interval 0 to 1, and you let the vector space be the set of continuous functions on this interval. So that is to say, real valued functions. So these are functions from, these are functions which take the interval to R. And you define the inner product of two functions by an integral. Okay. I claim that that is an inner product on this vector space. So let's think about that for a minute. So first of all, this is a vector space. You can add functions and you can multiply functions by scalars and so on. So this is certainly a vector space, and I'm claiming that this is an inner product. So for example, one of the things I need to check is that I need to check that the integral of f1 plus f2 times of x times g of x had better be equal to the integral of f1 times g plus the integral of f2 times g, right? Because this is f1 plus f2 inner product with g, and that had better be equal to f1 inner product with G plus F2 inner product with G. So this is one of the properties I need to check. And if I write it out, what I need to check is exactly this identity. And is that true? Well, yes. It's one of the basic properties of integrals that this is true. If you add functions and multiply this way, you can break it up into two. So that's part of the requirement. Let's see. It's clear from this that this is symmetric. The integral of f times g is the same as the integral of g times f. So that's clear. And what about positivity? Well, let's see. Positivity. Is it true that ff is greater than or equal to 0? Well, that would say that's exactly the same thing as saying f of x times f of x is greater than or equal to 0. This is the integral from 0 to 1, which is to say the integral of f of x squared dx from 0 to 1 is supposed to be greater than or equal to 0. And is that true? Well, of course. This is f of x is a real number, so f of x squared is greater than or equal to 0. And if you integrate a positive function or non-negative function, you get a non-negative number. And what about the business about it being equal to 0? I need to know that the integral of f of x squared is equal to 0 only if, well, if and only if f of x is just the 0 function. Is that true? The only function whose integral is 0 is supposed to be the 0 function. Well, think about that. That's true. I'm talking about continuous functions here, so not that it matters that much, but anyway, this is true. So this is an example of an inner product, and this is a really fundamental example. And notice that there's no sum over a basis, or you're not taking summation xi squared or anything. This is totally abstract, but it has all of the properties that you're looking for. So this is a key situation where if you try to write it down and make it look like the ordinary dot product, you basically can't. But abstractly speaking, this is exactly the right thing. It has all of the properties that you would expect. Okay, so let's go on now and talk about some other properties that the dot product has. And there's an important type, which is there are various inequalities that inner products satisfy. So let's go back to the dot product in R2 specifically now. I don't know if you all remember this formula, but if you take the dot product of two vectors, that's the length of v times the length of w times the cosine of the angle between them. This is sometimes called the law of cosines. And I'll illustrate this, basically prove it. It basically comes down to, suppose that you have unit vectors. Suppose you took two vectors with length 1. Then the formula says that their dot product is the cosine of the angle between them. And it just by rotating, you can reduce it to the first vector being just 1, 0. And then you have the circle. And your other vector is some other vector. And this is the angle theta. And this is the point cosine theta, sine theta. And if this is V and this is W, then V dot W is, well, 1 times cosine theta plus 0 times sine theta. And that's what I was claiming. And that's basically the proof. This you also have to check that this scales correctly when if you stretch V and W, it has the right property. But that's the main idea. And notice that one thing that this says is if you give me a vector V, and you ask me to find another vector W with 2 properties. I want them to have the same length, and you want to maximize the dot product. Well, if you look at this picture, if you think of V as being this vector and this as being W, you're allowed to choose any W on the circle, and then the dot product would be the cosine. And clearly the way to maximize that is to take theta is equal to 0, and in which case V is equal to W, excuse me, theta is equal to 0, and that makes V is equal to W, and the maximum dot product that you can have is the length of V squared. So let's look a little bit more at this. So we have this identity. Excuse me. In the case of the dot product, I said that V dot W is the length of V times the length of W times the cosine of the angle between them. And of course, well, what I just said is that cosine is always less than or equal to 1. And on the other extreme, it's always, of course, greater than or equal to minus 1. And so if you think about it, what that says is that the biggest that V dot W can be is the length of V, the norm of V, times the norm of W. Is certainly less than or equal to the norm of V times the norm of W, because cosine theta is less than or equal to 1, and it's greater than or equal to minus that. So in other words, the absolute value of V dot W is less than or equal to the norm of V times the norm of W. So this is a very famous inequality, and it holds in general. So let me state that. This is the Cauchy-Schwarz inequality. And it says if you have a vector space V and any inner product well, then you define the norm as usual, and then you have this inequality. The absolute value of V dot W is less than or equal to the length of V times the length of W. So this is one of those formulas that you should inscribe somewhere on the back of your hand or something. This is always remember this. For any inner product, the dot product, excuse me, why did I do that? Sorry about that. It's of course any inner product. The inner product of two vectors, the absolute value is less than or equal to the length, the norm of V times the norm of W. Now keep in mind that this number over here, of course, is non-negative. The length, the inner product of V and W could be negative, but anyway, that's why you need the absolute value. But in absolute value, it's less than or equal to that. Okay, well, I just realized I've been talking for 28 minutes, so I'd better stop. There you go, and I'll see you in class tomorrow.